So thank you very much, Marachi, for this kind introduction. And thank you, of course, very much for the organizers for really making an effort in organizing such an interesting conference. The talks until now have been fascinating and I was really enjoying them. Due to lack of time, I'll just start. First of all, we have a list of different ingredients here. I know you're all probably hungry because lunchtime is approaching rapidly. But my main thought question would be here, what would you get from all of these different ingredients? And I mean, if you look at them, there's flour, sugar, milk, and other stuff. So this might be some sort of baked goods or something like that. So the first thing you can get is maybe just all the ingredients separated individually. You can stare at them and do nothing, or you can decide to do something with them. And then, for example, you would mix them and then you would get some sort of batter. You can then decide, okay, I'll leave this batter alone and eat the batter as is. Or you can maybe say, I'll apply some heat to it and then get a nice vanilla cake. And then if you really have enough energy, you can do some post-processing on this cake, and then you'll end up with a really nice fancy cake with different layers and a lot of different creams. Of course, there are situations where the post-processing doesn't work out too well, or you apply too much heat and you end up with a burnt cake, which you really can't eat. Or maybe you don't have enough of each of the ingredients, so you only have half a cup of sugar or half a cup of milk, and you end up with cookies instead of cake. Or for example, let's say we're in a situation like 2020 when COVID-19 is wreaking havoc all over the world. And basically, we don't want to go to the supermarket and get all our missing ingredients. So we don't have baking soda or we don't have white vinegar, and we end up with a loaf of bread from these ingredients instead. So slight changes in the processing or slight changes in the ingredients really have a rapid change on, or a large change, I would say, on what you end up obtaining. And this is exactly the method that I use to do my research, which is combinatorial material science. And this is basically a cycle type of research where you have a variety of steps, which include high throughput fabrication and high throughput analysis, inserting information into a database and designing of new experiments from all of this. And actually, combinatorial material science has proven to be very good when looking at compositional changes of material and discovering new materials, for example, for photoluminescence, shape memory alloys, or high TC superconductors. So you can see that as you increase the complexity of the elements, so more elements in this case, you actually get interesting results. And what I wanted to do in this work was be able to combine this with one of our methods that we use at the Max Planck Institute, which is glancing angle deposition. And I'll explain a little bit about it now. So it's a PVD method where it can be done in a sputtering system or an E-beam system or any other PVD system. However, the main difference is that our substrate is not parallel to the source of your material. It's actually tilted at an angle called alpha, and these are very high angles, so usually above 80 degrees, usually between 80 and 90 degrees. And you can tilt this angle and change it, and also change the rotation. This angle allows for actually what is called shadow growth. So you end up with different kinds of grains, that these grains shadow the incoming vapor flux, and then they end up forming varieties of rods and nano shapes, so zigzags, helices, and all these different things that you can see over here. And in our lab, we've actually been able to obtain several types of shapes, single shapes on one substrate. So we deposit only one type of nano shape, for example, these nano hooks, nano zigzags, and nano barcodes, which each were deposited separately on individual wafers. So what I wanted to do was take combinatorial science, combine it together with glancing angle deposition to be able to control compositional changes, structural changes, surface structure, and any other variant you can think of that might come out of this type of deposition, and then be able to understand and analyze all of this information. So how composition and shape and other things affect certain types of applications and activities and properties in these samples. So the way that I did it was insert a special type of barrier into our chamber, and this barrier had to be optimized. So this is a front view of what it would look like, and this is a side view of what it would look like. So you see that basically from the side, your crucible containing the material or the material source is completely covered, and from the front view, it's partially covered, where you have a certain distance of how much is exposed of your material source and also the barrier height have a big effect. So we did some different Monte-Carlo simulations with ballistic shadowing models in order to be able to optimize this. And we were actually able to achieve quite a nice gradient in the vapor flux, which led us to linear thickness changes, which are quite important because then we know that one area we have a little bit of material and in the other area we have a lot of material. And this of course depends on the vapor flux as well as the alpha angle that we use in the deposition chamber. So in order to increase the complexity now, we inserted two sources, one across from each other, both with optimized barrier positions to obtain the linear gradient flux in our vapor in the PVD system. And then we co-deposit two different materials. But then we say, okay, this is just a binary system. We want a multinary system where we can have a lot of different elements and study all these different elements. So we then rotate this sample by 120 degrees, deposit two more materials in a binary system, and rotate it again and deposit two more. So we end up depositing 6 different materials at 3 different phi angles, so rotation of the substrate around itself at the same alpha angle tilt. And this leads us to an octernary elemental materials library. It's octernary because some of the material sources had 2 or 3 different elements in them. And these sort of materials were actually chosen because they each individually show activity towards oxygen evolution reaction, which was the system that we wanted to study for this material library. So just from looking at a composition point of view, you can already see that there's high compositional changes throughout the library with the different materials coming off the different edges. So for the nickel corner, or nickel edge, where the nickel starts, the highest compositional element is nickel, cobalt, etc., and so on. And they're really spread out quite nicely from a compositional point of view. But what happens if you look into the nanostructure? So just from SEM images and measuring on the surface, you can immediately see that there are changes. So for example, the lanthanum oxide edge looks like some sort of strange triangle shapes, and the cobalt looks like these round globular shapes. So they're completely different. And when we look into the actual structures by TEM, you can see completely different nano shapes across the library. So you have an L shape, you have this bone or barcode-like structure, a match structure shape, zigzag, and the lanthanum and barium titanate are actually intermediates, and that's due to issues with their vapor flux. From just some EDX analysis on the different structures from the different edges, you can see that some of the elements really interdiffuse. They're completely oxidized, first of all, but some of them interdiffuse. So for example, barium, lanthanum, and titanium interdiffuse throughout the whole area of this of the nanostructure in all the shapes. But if you look at nickel, for example, or cobalt, they're very localized into small cluster areas. And this really happens for all the different types of shapes. So we then decided, okay, it's time to examine this interesting library that has really big compositional structures and really large nanostructural changes, and see what their oxygen evolution reaction capabilities are as an electrocatalyst or electrocatalysts, because it's a lot of different materials. So first glance, we can see these are just the different edges of the library, and they're marked over here so you can see what they look like. It looks like there's really no big changes on the library with regards to the overpotential that's needed for oxygen evolution, which is quite surprising because we would have expected large changes since we have both structural changes as well as compositional changes, so the chemical environment should have an effect. And indeed, sorry, I think I'm frozen.
You are not frozen.
Oh, okay, sorry. And indeed, if you look at the map of 25 points that we scanned all over the library, the overpotential really doesn't change dramatically throughout the library. Yeah, it changes maybe from the cobalt to the molybdenum edge or from the molybdenum to the chromium edge, but the changes are only around 40 millivolts, which is quite small. So we expected much larger changes. And then if we look into the CVs, we see something really interesting. So actually all of the CVs from the different edges and all the CVs all over the library, except for one, which is in the cobalt edge, have this peak between about 1.3 and 1.4 volts versus RHE. And this is most likely the peak related to nickel oxidation. So either nickel +2 to nickel +3 or nickel +3 to nickel +5, which we both have based on XPS measurements in our library. And indeed, if we then look into XRD measurements, what we're able to actually see is, and these are XRD measurements over 9 points within the library, is that throughout the library, every single point shows actually nickel oxide as the dominant crystal structure. Some show additional crystal structures, which we haven't figured out yet, but all of the points show nickel oxide. So our theory is that the nickel oxide clusters become very dominant in the activity. And what we did also to further look at this is again, re-examine the TEM images, and you can really see that the nickel oxide is situated in clusters within the different nanoshapes. So these nickel oxide clusters would not have formed had it not been for the nanoshapes. So they're really situated in tiny areas throughout these nanostructures and nanoshapes on the library. So these nickel clusters seem to be the dominant factor. And then what we decided to do was synthesize just nickel oxide nanorods in the same system without using this gradient flux. And you can see that these rods are actually composed of small nickel oxide particles. So this is the LSV for these nickel oxide rods, and it's actually much higher than for the whole library. So this means that we have higher overpotentials when we're just using nickel oxide, but when nickel oxide is placed inside these nanostructures in these slightly different chemical environments, it has much higher activity towards OER, reduced by even 90 millivolts. So it's a really large reduction for just changing the structure of the nickel oxide clusters within the nanoshapes. We then also went on to synthesize one library that didn't contain.
Yes. Give 2 more minutes. Okay.
Okay. We went on to synthesize a library that didn't contain any nickel at all, and immediately we see much larger variations of 90 millivolts between the different edges, which is what we expected to see. So this is more of a compositional effect versus what we saw before, which is more of a nanostructure effect. And indeed, if you compare the overpotentials for the different libraries, so you can see that for the sample that contained the nickel, the overpotentials were much lower, and for the sample that didn't contain the nickel, the overpotentials were much higher. So if we just compare the TAFL slopes, relative values, not full values, because we had very high scan rates for these measurements, you can see that really they're very similar throughout the library that contains the nickel, meaning that the mechanism is the same. And furthermore, the nickel oxide nanorod pure sample also has a very similar TAFL slope. So the mechanism is similar, meaning that in the library that contains the nickel, these nickel oxide nanoclusters are the active component, and they are what's dictating the activity towards oxygen evolution reaction. But if you look at the sample that does not contain the nickel oxide, the nickel inside it, so we already see quite large changes in the TAFL slope, meaning that the chemical compositions play a more important role over here as the active components towards oxygen evolution. And even more so, you can see that the trends are quite similar. So we first have a reduction and then an increase for both libraries. So the chemical environment does have an effect in the library containing the nickel as well, but not such a high effect as the nickel oxide nanoclustering within the nanostructures. And with that, I would like to summarize. I hope I convinced you that this combination between glancing angle deposition and combinatorial material science is a really interesting way to form different gradients in composition and nanoshape. And then we were able to see that the nickel oxide actually forms tiny clusters, which are much more active towards oxygen evolution. But we do also have a compositional effect as well as a structural effect. So just changing one component, in this case nickel, led us from having a very beautiful cake to having bread, or whatever you want to call it, in comparison to what we looked at before. And with that, I would like to thank everyone who worked on this project. They're all marked here with arrows, and our collaborators, Professor Alexander Kuhn and Dr. Salinas from Bordeaux University, collaborators from Bar-Ilan University, and thank you very much for your attention.
Thank you, Hannah-Noa. If there are any questions, please ask. Otherwise, okay, so I want to thank Hannah-Noa and all the speakers again. Then we should have a break and move forward to the next session, which you can go back to your program and click on the Intel tutorial session that should start within 15 minutes or so. So this is a break of 15 minutes, and then we will all meet in another Zoom Thank you for all the speakers and all the attendees. Very nice presentations. Thank you very much.